Hi there. In today's lecture, we're going to be starting on sequences. Okay, so this is a new chapter that we're going to be going through. So firstly, what is a sequence? So technically speaking, a sequence is a map or a function, let's call it x, that maps the natural numbers into the real numbers. So these would be examples of real number sequences. However, this target space over here, the reals, we can replace that with other things, and then we would get sequences of that. For example, we can replace it with the set of polynomials, and we can have sequences of polynomials. We can replace it with integers, and then we will have sequences of integers, and so on. Okay, so there's many different variations that we can use. Okay, but for our purposes, we're going to be having sequences of real numbers. Okay, so what this does is it takes a natural number n and maps it to some real number that we call x sub n. Okay, and typically we write these sequences as an infinite list of the particular values. For example, we can have the sequence xn is equal to 1 over n, so that's like the functional form, but typically we would write it as 1 over 2, 1 over 3, dot, dot, dot. Okay, so it's an infinite list of terms. Okay, so this is what we call a sequence. Okay, and of course this these terms can be real numbers, rational numbers, anything like that. But in general, we're going to stick to real numbers. So that's what you can assume from now on. Okay, so the first few things that we can think about regarding the sequences are various behaviors of sequences. So how do these sequences behave? Okay, so if you just imagine different types of sequences, can we classify them by their behavior? So what do I mean by behavior? So firstly, we can think about some very simple sequences, the simplest types of sequences, and those are constant sequences. So this is when our sequence is equal to some constant, let's say 3, for any natural number. So here we just have a list of 3's. So this is a sequence. It's a list of numbers for every natural number. We have an element in the sequence, and it goes off to infinity. So this is definitely a sequence. It's not a very interesting sequence, but it is something to think about. Okay, number 2, we could have sequences that go off to infinity. So sequences that go off to infinity. Okay, so we're not being very precise with this. We're just thinking about how could these sequences behave. Later on, we will be a bit more precise about what we mean by these different things. So as an example with this, we could have the sequence 1, 2, 3, 4, dot, dot, dot. Okay, so this sequence we know is going to get bigger and bigger and bigger, and it's going to go off to infinity. Of course, we could have something like -1, -2, -3, -4, dot, 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 and that would go down to minus infinity. So if we just look at a little picture of what's going on, we would start off at 1 and then just go off like this. Okay, or for this other picture here, we would start off at -1 and then go off like this. Okay, so in either case, these sequences go off to infinity. Okay, another type of behavior that we could get is sequences that level off to a constant. Okay, so what do we mean by this? Well, we mean that at some point the sequences level off, so they approach some sort of constant. For example, we could have 1/2, 1/4, 1/8, and so on. We see that as this denominator gets bigger and bigger, the fraction gets smaller and smaller, and we can see eventually that this is going to go down to 0. So if we draw a little picture of what's going on, the sequence starts off like this, and then if we just look at it in terms of these dots, if we imagine these dots as the elements in the sequence, we see that the dots go down closer and closer to 0. Okay, so that's what we mean by level off to a constant. Of course, it doesn't have to be 0. It could be something else. We could have a situation like this, where the sequence might do something like this. Okay, so it doesn't look like it's leveling off to a constant, but then after some point, let's say capital N, maybe it does this. And then we see that before this capital N, the sequence is going up, it's going down, it's doing all things, but then after this capital N, we see that the sequence starts leveling off to a constant. Okay, so this is what we mean. We mean that after some point, the sequence approaches some constant value. Okay, so it doesn't have to do that right away. Maybe after some n, whatever that may be, then after that point, it might go off to become a constant. Okay, so before this capital N, it could do something else, but we're looking at the long-term behavior. What happens when our sequence goes off here? So when this n, the little n, goes to infinity, what happens to the sequence values? Okay, so that's something else that can happen. Or, doesn't have to do that, it could alternate forever. Or form some cyclic pattern. Okay, so something to imagine, like the sine function or the cosine function, it could increase for a bit, then it would decrease for a bit, maybe it increases a bit again, and then decreases a bit again, and then it does this forever. Okay, we've got this cyclic pattern of our sequence elements getting bigger up to a maximum, then getting smaller down to a minimum, then going back to a maximum. So it never stabilizes. It just repeats this pattern. So it never stabilizes or approaches a constant. Okay, so that's another type of behavior. Okay, we've got this cyclic pattern. Of course, we could have something else very similar to this. We could have just alternating between a few elements, for example. So here it alternates between a few elements, but it doesn't have to have this sine function pattern. It could just be something like this. So maybe we're at 1, and then we're at -1. Then we're at 1, and then we're at -1. And then we're at 1, and so on. So here we don't have this exact sine function that we expect to see with cyclic patterns. Maybe it just alternates between two elements. So it starts off at 1, then -1, then 1, -1, 1, -1. So all the elements between 1 and -1 are missing, okay, unlike a sine function where it's filled in. Okay, but this is still alternating. We've got this pattern of 1, -1, 1, -1, and it never stabilizes at some constant. So again here, it just always alternates, never approaches a constant. Oops, sorry, constant. Okay, so again, we've got this alternating behavior. Okay, so these are just some of the behaviors that you should look out for when we're looking at sequences. So we can either have constant sequences where it's just fixed value forever. We could have sequences that go to infinity, sequences that go to minus infinity. We could have sequences that level off to a constant, so it might just be a gradual decrease to a constant or a gradual increase to a constant. It may have some other behavior and then go to a constant, like we have in this picture, or it might never go to a constant. It might go up and down in a cyclic pattern, like with the sine function, or it might just alternate between 2 points, so like 1, -1, 1, -1, and so on. So these are just different behaviors that you should think about. Okay, so this is just something to think about. It's not precise. What we're going to look at now is the precise definition of these behaviors. Okay, so definition. So first, this constant sequence, we don't need to do any extra work with that. If it's a constant, then there's not much we can do. Okay, so it's a very, very simple sequence. However, these next two cases, the ones that go to infinity and the ones that go off to a constant, we have special names for those two. Okay, so definition. A sequence is called convergent if the limit of the sequence, so when we say lim xn, what we mean is the limit as n goes to infinity of xn. So if this limit exists, and finite and all of that, so we end up with some nice constant. If this limit exists, okay, then we say that this sequence converges. And we can say it converges to some value x, which is our limit value. Okay, so that's what we mean by convergent. So that would be this case number 1, a constant sequence that is convergent. Since all of the elements are the same, and all of them are 3 in this case, we know that the limit value is 3, and so it must converge. However, in the second case, the limit value is infinity. This top one goes off to infinity, this bottom one goes off to minus infinity, so it doesn't converge. It doesn't go to some nice finite value. However, for these cases, in number 3, we see that both of these here, they converge. So the first one, that converges to 0. The second one, it may have some behavior before this capital N, but eventually it converges. So in the limit, it converges. So eventually converges to a constant. Okay, and we call those sequences convergent. Okay, else the sequence is divergent, or the sequence is called divergent. Okay, now you mustn't get confused with this word divergent. So we know that these sequences here that go off to infinity, we know that those diverge, like when we looked at just functions diverging, we know what that means. However, with regards to sequences, that is not the only case. So it is true that sequences that go off to infinity are divergent, but it's also the case that alternating sequences are also called divergent. Okay, so even though these alternating sequences don't go off to infinity, the fact that they don't converge means that they are divergent. So divergent is not only going off to infinity, it is also including the alternating sequences. So not only infinite sequences, so not only infinity, but also sequences that alternate. Okay, so you may have a sequence that is always finite. Okay, it's always between two bounds, but if it never stabilizes, we also call it divergent. Okay, so sequences that go off to infinity and alternating sequences, those are both divergent. Why? Because they're not convergent. If it's not convergent, it's automatically divergent, just by the definition. Okay, and this gives us a nice way of checking if a sequence is convergent or not. We look at this limit. If this limit gives us a nice value, then it is convergent. Okay, let's have a look at some useful properties of these convergent sequences, and we can use these properties when doing our calculations. Okay, properties, and then a big exclamation mark. These are for convergent sequences. So if the limit an and the limit bn exist, then. So we have this big statement before all of these properties. So if we have a sequence an and a sequence bn, both of them must be convergent for us to use these properties. So if either of these do not exist, then we cannot use these properties. So please remember this stuff in the box here. This needs to be true before we even look at any of these properties. Okay, so again, let's put more exclamation marks there. It's very important that both of them exist before you start applying these properties. Okay, so with that out of the way, let's look at the first property. So this says that the limit of an plus or minus bn is equal to the limit an plus minus the limit bn. Okay, so very similar to the limits of functions. But here, this little n, that is a natural number, not a real number, like you did with functions of x. Okay, so please just keep that in mind. But you'll see that a lot of this behavior is very similar to limits of functions, and we will see that we will use some of those examples that we did with functions. Okay, number 2. Limit of c times an, where c is a constant, we can take that out. Again, very similar to limits of functions. Number 3, limit of an times bn is equal to the limit of an times the limit of bn. So we can separate this out into two limits. Number 4, we have the limit of an over bn. Again, just note this bn, that can't be 0, or else we're dividing by 0, and that will be a problem. So the individual bn's, they can't be 0, and also for this to work, we have the limit an over the limit bn. The limit cannot be 0 either, okay, because then we're dividing by 0, and that's also an issue. So even if the individual terms are never 0, for this left-hand limit to exist, on the right-hand side, the limit can't be 0. So just a note, like we had 1, 1/2, 1/3, ... Each of these terms are non-zero, so that means the left-hand side is fine, but for the right-hand side, the limiting value is 0. So in the limit, this is 0, and then we're dividing by that, and that's going to be a problem. Okay, so please just look out for division by 0. Okay, that's number 4. Number 5. Okay, so another property that we're going to be using is if we have the following: for all n greater than or equal to capital N, if an is less than or equal to bn. So for all of these values above a certain point, if the b sequence is always above the a sequence, then the limit values also satisfy this inequality. Okay, so if the individual elements satisfy the inequality, then the limit values also satisfy this inequality. Okay, so we'll be using this quite a bit to answer the different problems. And then with this, we can also extend this a little bit to use the squeeze theorem. So if we have an less than or equal to bn less than or equal to cn, if we take the limit throughout, and we have, let's say, the limit an is less than or equal to the limit bn less than or equal to limit cn, if the far left and far right limits exist and are the same, then the middle limit will take on that value. Right, so this is just a recap of the squeeze theorem. Okay, but you've covered that previously, so I won't go into that with too much detail. Okay, but the squeeze theorem, that carries over from functions into sequences. Okay, and number 6, the last property that we're going to go through today. We may add more properties later, but these should be enough to answer some questions. Okay, so let's say f is a continuous function. Okay, so we know what continuous function means. That was covered last year. So let's say f is a continuous function, then if if the limit of xn exists, so we have some sequence xn, if the limit exists, then the limit of f of xn, so now instead of taking the individual xn elements, we take the limit of the function of those elements. Okay, this is equal to f of the limit of xn. So what this means is that if our function f is continuous, then we can take this function, we can take this limit inside the function. Or if you want to think of it the other way around, we can take the limit outside the function. Okay, so in other words, we can interchange the limit and the function. So we can have the limit on the outside of the function, or we can write the limit on the inside of the function. Yeah, we can swap them around. We will be using that quite a bit. Okay, so if we know a certain function is continuous, then we can do this rearrangement here, and this makes things quite nice and easy to work with. Okay, so those are all the properties that we're going to look at for now. I'm going to go through 4 examples just to illustrate what we do, and then in the next lecture tomorrow, during our single period, we will go through some more complicated examples and some more properties. Okay, so let's have a look at some examples. Okay, so number 1, an is equal to n minus 1 over n plus 3. Okay, so this is a sequence. Here we have just defined what each element is going to look like. So we can substitute different values of n, and we will get different values of an. So just as a little example, if n equals 1, we're going to get 1 minus 1 over 4, so that will be 0. if n is equal to 2, we're going to get 2 minus 1, which is 1. So we can write that as 1 over 3 plus 2, that's going to be 5. If n is equal to 3, then we're going to have an will be 3 minus 1, so that will be 2. And then 3 plus 3, that will be 6. Okay, or we can simplify that to 1/3. Okay, and this can continue. So what we want to see is the behavior of this sequence. So does it converge? Does it diverge? If it converges, what does it converge to? So these are the questions that we're going to be seeing. So does the sequence converge or diverge? If it converges, what does it converge to? Okay, so these are just some questions that we ask. Later on, we will have more questions that we ask, like, is the sequence bounded? So in that case, we're looking for either like an upper limit for the sequence. So if n goes to infinity, the sequence never goes beyond a certain point. So maybe that is above or below a certain point, it's bounded. Things like that we're going to be looking at later. So for today's lecture, we're just looking at convergence, divergence, and if it is convergent, what does it converge to? Okay, so let's have a look. So here, if we just substitute n equals infinity just as is, we're going to run into a problem, because in the top we're going to get infinity, in the bottom we're going to get infinity, and that's a problem, right? That's one of those indeterminate forms. So as is, we can't just substitute, or we can't just take the limit. So we can do a little bit of manipulation, and we'll see that we can rewrite this in a way where we can take the limit. So here, let's just rewrite it as n minus 1 over n plus 3. We can write this as n times 1 minus 1 over n divided by n times 1 plus 3 over n. Okay, so in the top and in the bottom, I just factored out an n. So if you multiply in the top and in the bottom, you'll see we get back to the original. But here, we can get rid of this n, and we can get rid of the other n, and we're left with 1 minus 1 over n over 1 plus 3 over n. Now we can use our limit properties. So we've got a quotient. So let's look at the top and let's look at the bottom and see, can we take the limit of the top? Can we take the limit of the bottom? And is it finite? Is the bottom 0? Things like that. Okay, so let's look at the top. If n gets very, very large, then 1 over n is going to get very, very small. And in the limit, this is going to approach 0. Okay, and then in the denominator, we have something similar. We have 3 over n. Again, if n gets very, very large, then 3 over n will get very, very small. And in the limit, that will go to 0. So in the top, we're left with 1. In the bottom, we're also left with 1. Okay, so the limits exist, they're finite, we have no problem. So let's write this out properly. So we want to find the limit of an. Now, I'm not going to repeatedly write n goes to infinity because that is the default, right? We're not going to take any other limit besides that. So sometimes I'll just forget to write the n goes to infinity, but we know what that means. Okay, so this is going to be the limit as n, so this would be n goes to infinity, but like I said, we're going to leave that out, so this will be the limit an. So that will be the limit. We have our working here, so it will be 1 minus 1 over n over 1 plus 3 over n. And like we said, the top and the bottom limits exist, so we can separate this. So this will be the limit 1 minus 1 over n in the top, and we're going to have the limit 1 plus 3 over n in the bottom. And our previous working over here said that that was fine to do, so we're good with that. So this